So the first thing we talked about in chapter 13 was something called the rate law. All right, so in a question on the test is what is the rate law? So it's going to be in this form. Okay, rate is equal to K. So in this particular reaction, NH4 plus will have a concentration, and it decays as it gets converted to the products N2 and water. So that decay, we'll call it exponent A. The second reactant is NO2 minus. This is called nitrite, and it will decay to some order. We'll call it exponent B, and that too will decay from 2N2 and water. So in this particular question, on the practice test, we need to find K, and then we need to find exponent A and exponent B. So the first thing we want to do is compare. So just by my eye, I am seeing that we can compare experiment 1 and 2. Okay, so this is just by my eye. We can compare experiment 1 with experiment 2. So let's compare experiment 1 to experiment 2. Right, so that means rate 1 over rate 2. Okay, let's use this formula here, equals K times NH4 plus, okay, raised to the power A, times NO2 minus, raised to the power B. Okay, we'll do the same thing, making a comparison of the two rates. To the power A, NO2 minus to the power B. Alright, so rate 1 here is 7.20 times 10 to the minus 6 molarity over second. Just plugging stuff in here. 7.20 times 10 to the minus 6 molarity over second. Okay, divided by 3.60 times 10 to the minus 6 molarity over seconds. That is rate 2. So this is going to equal to K times NH4, ammonium ion NH4. And in rate 1, experiment 1, this is 0.24 molar. Okay, raised to the power A, because this is going to decay at a certain rate, 0 first or second. And then we have NO2 minus raised to the power of B. That will 0.10 molar, 0.10 molar raised to the power B. Okay, we'll substitute now these values here. K, and what is K? K is something we'll solve later. What is NH for positive? That's 0.12 M raised to the power A. NO2 minus is 0.10 molar raised to the power B. Okay, raised to the power B. So on the exam, we want to find K, and we want to find exponent A and exponent B. Alright, so the 0.24 to the power of A cancels, the 0.10 to the power of B cancels with the 0.10 to the power of B. So these guys cancel. And the K's cancel, we'll find that out later. So it's going to be 0.24 molarities cancel divided by 0.12. I'm going to take this to the power of A and this to the power of A and then move it outwards. The whole thing to the power of A. These units cancel, and 7.20 times 10 to the minus 6 divided by 3.60 times 10 to the minus 6 is 2. Okay, 0.24 divided by 0.12 is 2 to the power of A. Alright, so we compared experiment 1 to experiment 2. Rate 1 equals K and all the reactants over rate 2, K all the reactants, plugging everything in, substituting our values in from this table, and then moving the exponent out. 0.24 divided by 0.12 is 2. So 2 to the power of A equals 2. So what is the value of A going to be? Okay, so this tells us that NH4 positive is going to decay to the first power. Okay, ammonium ion decays to the first order. Okay. All right, now let's compare experiment 2 with experiment 3. So 3.60 times 10 to the minus 6 over 5.40 times 10 to the minus 6. So all right, K, well, look at that later. NH4 to the power of A. So what is NH4 for experiment 2? Okay, 0.12 molar raised to the power of A. Okay, we all know A is 1. What is NO2 minus for experiment 2? Okay, 0.10 M raised to the power of B. And then experiment 3. Experiment 3, what is NH4 positive for experiment 3.12 big M? And what's NO2 minus raised to the power of NO2 minus for experiment 3? Okay, it's going to be 0.15 molar raised to the power of B. Just put this up here. Alright, so the 0.12 molar to the power of A cancels with the 0.12 molar to the power of A. Okay, you can see that right here. These guys cancel. And then I'm going to push this up 1. I'm going to move the exponent up. This is what I mean when I'm talking about 0.12 to the power of B, 0.15 to the power of B. It's just 0.10 divided by 0.15 to the power of B. I just moved that exponent upwards. And what's 3.6 times 10 to the minus 6 divided by 5.40 times 10 to the minus 6? What is that on our calculator? 0.6666. 0.6666 is 2/3. Okay. What's 0.10 to the divided by 0.15? It's also 2/3. Okay. So 2/3 to the power of B equals 2/3. So what will B equal to? 1. So just like NH4 positive, NO2 minus decays with first order. Alright, so now we have a rate law. Okay, and that rate law is going to be rate law is going to be rate is equal to K times NH4 positive, that's the ammonium ion raised to the first power, times NO2 minus raised to the first power. All right. So the overall order of the reaction is 2. Okay, first order decay for this reactant, first order decay for the second reactant. So the overall order is 1 plus 1 is 2. Okay, just in case you see that. The overall order of the reaction. You add the exponents. All right, so we're not done yet. We have to find K. So we'll pick any experiment. So which one would you like to pick? 1, 2, or 3? I'll pick 1. Okay, I'll pick 1, experiment 1. But you can pick 2 or 3. So we will use experiment 1 to find the value of K. Almost done. We just need to find K. We'll use experiment 1 values to find the value of K. All right, let's go ahead and do that. So what is rate for K? The rate for K is 7.20. The rate for experiment 1, I'm sorry, is 7.20 times 10 to the minus 6. Okay, so experiment 1, 7.20 times 10 to the minus 6. Molarity over second is the rate, which is, so remember, I'm just plugging everything in here. Okay, so experiment 1 values. So what's NH equals K? What is NH4 positive for experiment 1? Okay, it's going to be 0.24 big M raised to the power of 1. And what's NO2 minus for experiment 1? It's 0.10 raised to the power of 1. All right, so K is going to equal to 7.20 times 10 to the minus 6 molar divided by 0.24 m raised to the power of 1 times 0.10 m raised to the power of 1. And don't forget, it's molarity over seconds, so there's a seconds in here. So M's cancel, so we're getting K equal to, what's 7.20 divided by 0.24 times 0.10. Okay, that denominator is by its, 1 unit. So 7.20 times 10 to the minus 6 is this number, divided by 0.24 times 0.10 and 0.0003. Okay, what are the units? M in the denominator, seconds in the denominator. Okay, M in the denominator, seconds in the denominator. You can also write it like this on the exam, 0.0003 m to the minus 1 seconds to the minus 1. Okay, this or this is okay. So our final answer is going to be, this is what I want you to report on the test, okay? Okay, rate is equal to K, which we found out to be 0.0003 m to the denominator, molar in the denominator. So I'll just go m to the minus 1 seconds to the minus 1 times NH4 positive raised to the first power, okay, times NO2 minus raised to the first power. So this is the final answer. Okay, so you want to make sure your units are correct as well. Okay, and the units here are going to be m to the minus 1 seconds to the minus 1. Okay, so so we got the rate law, we got the value of the rate constant. So what is the rate when the concentrations of NH4 positive, ammonium ion is 0.39 molar, and NO2 minus is 0.052 molar? So how will we solve for part C? The way we solve for part C is just by plugging in NH4 plus into here, raised to the first power, and NO2 minus to here, raised to the first power. So let's go ahead and do that. Okay, part C is going to be rate is equal to K, which is 0.0003 m in the denominator, seconds in the denominator. What's the concentration in part C? 0.39 molar raised to the first power. And what's the concentration of NO2 minus in this problem? 0.052 raised to the first power. Okay, so this m in the denominator cancels out with this m in the numerator. So what's 0.0003 times 0.39 times 0.052? This will be our answer. 0.0003 times 0.39 times 0.052. 6.1 times 10 to the minus 6. And then don't forget our units, molarity per second. Right, so this is our final answer for this. And you just plug it in. How do you know this is the right answer? You can plug experiment 2 values in or experiment 3 values in. So let's say I plug in experiment 2 values. So what is NH4 positive in experiment 2? 0.12. 0.12. Okay, what is NO2 minus? 0.10 raised to the 1 power. That times 0.0003 m minus 1 seconds to the minus 1. Okay, so just verify using experiment 2 numbers. 0.10 times 0.12 times 0.0003. 3.6 times 10 to the 3.6 times 10 to the minus 6. .6 times 10 to the minus 6. Yep, 3.6 times 10 to the minus 6. So I know this is the right answer. Yep. put in experiment 2 values. I put experiment 2 into this rate law, and I got the rate. So this is the right answer. Right, so something like this on the exam. Right, so make sure you are good and proficient and comfortable and confident in doing this type of problem. All right, so something very similar to on the exam. All right, let's do another math thing that's on the test, and that is the ice table. Right. So we will be doing a lot of ice tables from here on out. So let's do another ice table problem. Right, what is the equilibrium concentration of hydrogen iodide, I2 and HI in this equation? So are we talking about an equilibrium here?
There's the one on the next page, but
I'm sorry?
like on the very next page, on the back of that first page, there is.
Okay, we'll do that problem.
But we don't have to do that.
That's fine. I gotta go back. All right, so this is a plug-and-play problem that will be on the exam. So we just plug in the rate constant K1 at its temperature T1, and then we'll plug in the rate constant K2 at temperature T2. We'll solve for one of those. EA will be given to us in this problem. EA is, oh no, it's asking us to calculate EA. Okay. So a certain first-order reaction has a rate constant of this at 25 degrees C. If the rate constant K increases to that at 45 degrees C, what is the activation energy for this reaction? So here we have to calculate EA. I think you guys did this in the lab, one of the lab reports. So K1 is 1 times 10 to the minus 3 at 25 degrees. So it's going to be 0.001. Okay. K2 is 3.5 times 10 to the minus 3 at 45 degrees, so they raised the temperature from 25 to 45. All right, so we want to calculate EA. R is given to us as 8.314 joules per mole Kelvin. And then 1 over T2 is, we're going to put this in Kelvin. So what's 45 plus 273? 318 Kelvin. Okay, what's T1? This is 298 Kelvin. So here in this problem, we have to calculate the activation energy EA. So I'll just do this first here. So natural log of this fraction. So let's compute that fraction. Okay, that's the fraction. Let's take the natural log of it. It's going to be minus 1.257 minus 1.25276, something like that. Okay, I'm just putting in some extra digits in there. Okay, equals EA. Let's do this fraction minus this fraction and divided by 8.314. Okay, the kelvins cancel. So 1 over 318 minus 1 over 298 minus parentheses 1 over 298, close those parentheses. Okay, equals this negative sign. So all this fraction minus this fraction equals this. Take this and divide it by 8.314, which is a constant. So I am getting minus 0.1, 2, 3, okay, 4 zeros, 2539. Okay, I'm putting some extra digits in there. Okay. Right, my final units are going to be joules over mole, because that's what an activation energy is. It's some joules over mole. Okay, so make sure you put in those units at the end of the problem. All right, so minus 1.25276 divided by minus 0.12342539 equals activation energy EA. Okay. And then actually, if you put if you cross multiply, the joules go here. If you cross multiply, the joules go here, and then the moles in the numerator, because it's in the denominator of the denominator, puts it in the numerator, and then when we cross multiply it, we'll get joules per mole as our final units. So just recognize our final units are joules over mole. So negative 1.25276 minus 0.12342539. Close those parentheses. What did you guys get? 49,341 joules over mole. Okay, so that's the answer I'm getting.
I somehow got lost to get the 0.0002 boundary. It's not like
1 over 318 minus 1 over 298. So that's this, and then we're going to divide it by 8.314. I think you may have forgotten to divide by 8.314 according to the formula, right? So I'll give you the formula and the constant. Let's double check and see if I am correct. Yeah. So I think we're good. 1 over 318 minus 1 over 298 divided by 8.314 is going to be this number. We have the EA in the numerator. There's a minus sign also. The minus signs cancel, and then EA is equal to this number divided by that number, taking this to the other side. And then 49,005 something, 49,531. And this is about 49.5 kilojoules per mole. Okay, so this will be your answer. So something like this on the exam, just make sure you're comfortable. You are comfortable using this equation. Okay? Make sure you're comfortable using this equation. Plug and play. Plug it in and get the answer out. Whether it's EA, whether it's K2. Plug it in and get it out. Okay. Here we solve for EA, and another iteration of the problem, another version of the problem, we solve for K2. Okay, so in our notes, we solve for K2. In this specific problem, we solve for EA. Okay? All right, I'll just wait 30 seconds or so before we move on to the next problem. And now we'll do the ice table. Okay, so now's a good time to do the ice table diagram. And let's go ahead and do that. So ice table is next. All right, we'll be doing lots and lots of ice tables from here on out, so this is good practice for what you will encounter after spring break, chapters 15 and 16. So we have an equilibrium, and then we have initially 0.035 molar of HI. Okay, so I'm going to rewrite this problem here, or rewrite this equation. The equilibrium constant is 50.5 at this temperature. So we have 0.035 molar HI. So if you have a bottle of 0.035 molar HI, okay, that bottle does not just contain 0.035 molar HI. What else is in the bottle? Okay, a little bit of H2 and a little bit of I2. So initially in this problem, you have 0.035 molar, okay? And initially in this problem, you'll have 0 and 0 of these two gases. Okay, so some of it is going to go this way because it's an equilibrium and the reactions can go either this way or the other way. So it's going to go this way because initially we started out with 0.035. Some of it is going to back react, and we're going to call that change, initial change in equilibrium, we're going to call this change minus 2x. We'll call this change plus x, and we'll call this change plus x. The reason why this change is going minus 2x has to do with the 2 here, okay, the stoichiometry. So at equilibrium, our final equilibrium is going to be x, and 0.035 minus 2x. So these are equilibrium concentrations. Let's plug it into the equilibrium expression to get our x, our final equilibrium concentrations. Okay, the reaction is going this way because initially you have 0.035, but after it settles at equilibrium, you'll get x, and 0.035 minus 2x. Alright, so KEQ is going to equal to HI squared. Okay, why do we square it? Because of the 2. This is the law of mass action. So we already, this is given to us that KEQ here is 50.5. Okay, HI is 0.035 minus 2x. We will square it. Divided by x and x. X here and x here. X times x is x squared. Alright, so to solve for x, we will take the square root of both sides of the equation.
Quick question. Can you tell me again why we squared the HI at the top again?
Yes, we can. We square the HI because there's a 2 here.
So that 2 still follows. Okay, thank you.
And it's minus 2x in the ice table, Royce, because it's 2 here.
I got you. Thank you.
Yes. Okay, so now we'll take the square root of both sides. Okay, the square root of 50.5 and the square root of this over this. Okay, square root of 50.5 we'll find it out in our calculator. Square root of 50.5. 7.106. I'll just add some extra digits in here. Okay, the square root of 0.035 minus 2x squared whole squared is just 0.035 minus 2x. And the square root of x squared, we're just going to call it x. Okay. X. Square root of x squared is x. Square root of this whole squared is this thing. Okay. All right, so we'll solve for x here. So 7.1063x is equal to 0.035 minus 2x. Okay, we'll move the minus 2x to the other side of the equation. So 7.1063x plus 2x is equal to 0.035. So this becomes 9.1063x is equal to 0.035, and I think we can solve for x here. 0.035 divided by 9.1063. And what is this on our calculator? 0.035 divided by 9.1063. 0.00384, big M, 0.00384. But what does that really mean? Okay, that is x, but what does that x really symbolize? Okay, this x really means is this x, which is the concentration of H2 at equilibrium, E. This x that we just calculated as 0.00384 symbolizes this x, which is the concentration of I2 at equilibrium, E. And then finally 0.00384x that we calculated is the concentration, once we plug it in here, the concentration of HI. So at equilibrium, our final answer, okay, the concentration of HI is going to be 0.035 minus 2x, but we calculated x as 0.0038. 0.00384. Okay, so what is that on our calculator? I'm getting about 0.0273. Okay, big M, molar. Okay, I'll take off points if you don't have the molar in there, and a lot of students just put it in without the units. So will we put the units in? And what are those units? Big M, which is moles over liter. So I plugged in x here, 0.0235 minus 2 times this is 0.0273. And then x here is H2, which is 0.00384. And then I2 here is 0.00384. Okay, so this is the answer you want to report on the test. Okay, how do you know this is indeed the right answer? Yeah, go ahead.
Oh wait, never mind. I didn't answer my own question.
Oh, that's good.
Because I was gonna ask, did we need, like at the equilibrium, because we have the 2HI, did we need to multiply the thing by 2? But then I see we did it. We have it there. Never mind. My bad.
All right. Yes, good. All right, how do we know we have the right answer? Okay, we'll plug in these equilibrium concentrations to here, and what should it equal? It should equal 50.5. Okay, so we'll plug in our final answer here, and it should equal 50.5. Okay, this is a way to check to see that the answer you got on the exam is indeed the right answer. So let's quickly do that here. 0.0273 squared Okay, divided by H2 is 0.00384 times I2, which is 0.00384. And I'm getting 50.5, which is, it's the right answer. Okay, so these are the right answer. Okay, why do I say that? Because I plugged all of these in here, and I regenerated the equilibrium constant of 50.5. So this is a way on the test you can check your answer to make sure it is indeed correct.
So also the 448 degrees Celsius, that's kind of just mute information, right? For the concept
Yeah.
of this problem.
All K's have to be given at a specific temperature.
Okay.
So that's all. If you change the temperature, you change K.
Okay.
Yeah.
The -2 is just because it's on the other side, it's on the
Because it's
higher
shifting
side.
left.
It's shifted left.
Yeah.
Okay.
And it's minus 2x because there's two HIs there. There's two of them.
And how did we know it was shifting left again? I'm sorry.
Because the problem tells us that we have 0.035 molar HI.
Okay.
And if it's 0.035 molar HI, some of that HI will go back because it's in equilibrium. So how much of it, to what extent it goes back, this is going to be the change. So initially, it's 0.035, which was given to us in the problem. The change, some of it will go back to give you I2 and H2. Some of it will go back. The reason why some of it will go back, Royce, is because it's in equilibrium. It's an equilibrium reaction. All right, so let's see if we can squeeze one more problem in. Back here. Let's do this one here. Yeah. All right, consider the reaction of this, and we have Kp at a specific temperature. So the reaction mixture contains this, this, and this. Find the equilibrium partial pressures of that at this temperature. Okay, so so these are gases, so they have a pressure. So the Kp here is going to equal to the pressure of I2. I'm sorry, the pressure of ICl squared, this is balanced, divided by the pressure of I2 times the pressure of Cl2. Okay, you see how I got that? Okay, products over reactants, and the squares because you have a 2 in here. Okay, and the P stands for pressure. Why did I say pressure? Because they're giving it in atmospheres. If they gave it to us in moles over liter, then you put concentrations, but they're giving it to us in pressures. Okay. And this has to equal to 81.9. Okay, they give us these pressures, so let's go ahead and plug them in here and see if they equal to 81.9. So ICl is 0.10, we got to square it. Okay, divided by pressure of I2, which is 0.10, times the pressure of Cl2, which is 0.10. So all of it is at 0.10, and I am getting an answer of 1. Okay, so this is not at equilibrium. Okay, this is not at equilibrium. So which way will it go to get to equilibrium, left or to the right? Okay, we're going to put Q first. Q here is 1. And then we're going to compare that to K. What is K? 81. Yeah. Okay, so which is bigger? This will be Q. This will be K. And which one is bigger? Yeah. Okay. So the alligator jaws point to the right. So this is going to shift to the right, okay, to get to the equilibrium. So initially, change in equilibrium. Initially, you're at 0.100. Actually, these are all at 0.100, okay? And this is going to go minus x plus 2x. Okay, everyone see that? So it's going to shift to the right because of the Gator rule. And it's minus x plus 2x, okay? And it's plus 2x because of the 2 there. Alright, so at equilibrium, this is 0.100 minus x, 0.100 minus x, this is 0.100 plus 2x. Okay, let's plug that in here to our Kp. So Kp is products. Okay, over reactants. And again, the square coming from here. Right, Kp is given to us in this problem as 81.9. And this is going to equal to 0.100 plus 2x squared divided by 0.100 minus x squared. Let's square root both sides of the equation. Okay, square root both sides. Okay, so what's the square root of 81.9? The square root of 81.9 is 9.049 or 9.050. And square root of this is 0.100 plus 2x divided by 0.100 minus x. Alright, so we'll solve for x.
There will be meetings soon, so it's
Okay. Alright, so we'll solve for x here, 9.050 times 0.100 minus x equals 0.100 plus 2x, and then we'll solve for this on when we come back from spring break. I believe our exam is Wednesday, right? The Wednesday of spring break, after spring break. So we'll finish this up, and then we'll finish up some of these questions as well. All right, so there will be no class on Friday. Okay, so I'll give you that time to actually catch up on this, and then I'll see you all after spring break. Okay, there's a science club meeting, so if you're interested in joining, stay up for that.